Hello and welcome to the Chemistry Made Simple podcast. I'm your host, Matthew Macario, and this is the podcast where you get chemistry confident and we take you from point A to grade A. Hello, welcome back. I hope you're well. Today we're going to be following on from the last episode where we talked about halogenoalkanes and their reactivity. And now we're going to talk about some of those reactions of halogenoalkanes. We're going to talk about nucleophilic substitution of halogenoalkanes. Firstly, I need to define what is a nucleophile and talk about a couple of examples. And then we're going to talk about what that reaction type is, how it proceeds, and we'll talk about some of the products that you might get from this kind of reaction with certain nucleophiles too. So firstly, let's define what a nucleophile is. A nucleophile is an ion or molecule that is able to attack and form bonds with a delta positive carbon or a fully positively charged carbon as well. In this case, we're going to talk about delta positive charged carbons because that's what exists in a halogenoalkane in the polar bond. A nucleophile gets its name because of nucleo for nucleus. It's attracted to nucleuses or positive charge, and phile because it loves positive charge. A nucleophile is going to be a negatively charged ion or a molecule with a delta negative atom, and that delta negative atom must have a lone pair that it can bond with as well. Some examples would be the hydroxide ion OH-. The ion has a negative charge and the oxygen has a lone pair, or more than one, but it has a lone pair that it can bond to the delta positive carbon. Another example is ammonia NH3. So this molecule has a delta minus nitrogen, and that nitrogen also has a lone pair of electrons that it's able to bond with as well. And a third example that we're going to look at is the cyanide ion CN-. Again, in this case, a negatively charged ion, and the carbon in this ion has a lone pair of electrons that it's able to bond with. And we describe the reaction type as a nucleophilic substitution. So the nucleophile is going to come in and substitute. It's going to replace the halogen atom because it's going to react with or attack the delta positive carbon of the carbon to halogen bond. So when this happens, the lone pair on that nucleophile will be attracted to the delta positive carbon. That lone pair of electrons will form a new bond with that carbon, and at exactly the same time, the bond between the carbon and the halogen will break or cleave with both of the electrons in that bond going with the halogen atom. Therefore, a negative halogen ion, for example Br-, will leave the molecule and a new bond is formed between the carbon that was in that bond and the nucleophile. So let's think about those examples that we mentioned earlier of nucleophiles. What products would we get? Well, let's consider the hydroxide ion first. So we can react a halogenoalkane with aqueous potassium or sodium hydroxide. We would do so in ethanol as well, so that the reagent and the halogenoalkane are able to mix together. And we do this at room temperature. When we do it under those conditions, the hydroxide will act as a nucleophile and will replace the halogen. So instead of a carbon to bromine bond, for example, if we started with a bromoalkane, we would replace that bromine with OH. So we would end up with a new bond between the carbon and the oxygen of the OH, and the product is an alcohol. It's an alkane with an OH group. And during the reaction, a halide ion, for example bromide, is lost from the molecule too. The reaction is very similar with cyanide ions, Cn-. The lone pair on the carbon of the cyanide ion is attracted to the delta positive carbon in the halogenoalkane. The lone pair makes a new bond with the delta positive carbon, and at the same time, the carbon to halogen bond breaks. It has to. Both electrons from the carbon to halogen bond go with a halogen atom, so a halide ion is lost from the molecule, and a new bond between what was the delta positive carbon in the halogenoalkane and the carbon in the cyanide ion is formed. And the product is a nitrile molecule. That's really quite a useful reaction because it increases the carbon chain length of the molecule by 1 by forming a nitrile. An additional carbon-to-carbon bond has been formed in that molecule, and that can be really useful for chemists who need to make a larger molecule. And then the third example of a nucleophile that we mentioned earlier was ammonia, NH3. This is a molecule, it's neutral. There is a lone pair of electrons on the nitrogen, and the nitrogen has a delta negative. The molecule is a little polar. During the nucleophilic substitution, the nitrogen of the ammonia molecule is attracted to the delta positive carbon of the halogenoalkane. Again, that lone pair on the nitrogen is going to form a new bond with the delta positive carbon. The bond between the delta positive carbon and the halogen then breaks at the same moment. The electrons within that bond going with the halogen atom to make a halide ion, which is lost from the molecule. But in this case, the reaction isn't quite finished, so we have a new bond between the carbon and the nitrogen. The nitrogen also has 3 hydrogen atoms attached to it, because ammonia came with its 3 hydrogens. Now the nitrogen has 4 bonds and is therefore carrying a positive charge. So the product isn't a stable neutral molecule, but an ion with a positive charge at the nitrogen atom. So what happens? One of the hydrogen to nitrogen bonds in molecule breaks, and both electrons go to the nitrogen atom, leaving a hydrogen ion or proton being released, and that is at the same moment attracted to another ammonia molecule that is in the mixture as well, therefore forming NH4+. So our products from this reaction are now an amine, a neutral organic molecule. There is the halide ion, for example, a bromide ion, and there is an NH4+ ion as well from that reaction. So what does this tell us? It tells us that we can use a number of different reagents, nucleophiles, to change one molecule, one compound, into a variety of different compounds. And this might be really useful if we wanted to create those compounds, or we wanted to use those compounds as a step for making other substances as well. This is something that happens very much so in laboratories and in chemical plants, to use the substances that are available to make substances that are wanted and more useful. Okay, so if you have any more questions on this topic, I'd be really happy to hear from you in the podcast Patreon community. So that's at patreon.com/chemistry made simple. Please come along and ask your questions there. You may also find me on Instagram at chemistry made simple. Great to hear you there too. Thank you for listening to this episode. I hope you found it useful, and if you have had value from it, do consider visiting our Patreon community at patreon.com/chemistry made simple, where you'll be able to ask deeper questions about this topic and get more support for your studies too. So I look forward to speaking to you again in the next episode, and until then, do look after yourself, and goodbye.